this topic, like laminar and turbulent flows, is very, very wide topic, and it requires a lot of discussion. So just to avoid that we are wasting your time, I would like to tell you that this webinar from the technical aspect will be more or less guidance according how to made this simulation in midas NFX. So I will be not focused on details. So please excuse me that. And because of, as I said, problematics is very complex. But it will be helpful to someone of you who already have some experience with NFX, and for you who is looking for some additional advising or for the way how to approach to this type of the problems. So that's all from my side, and now Cyprian will conduct the presentation.
Okay, thank you, Piotr. So I will present to you what we'll speak today in this webinar. So very briefly, we'll talk first about the CFD applications, because it's always good to review all the things you can do with CFD, and this will give you an idea of what you can do with midas NFX, and also using CFD to solve concrete problems. Then we'll talk about classification of flow types, we'll talk about laminar turbulent flow, and we'll show you some examples. And finally, we'll do some reviews about some industry applications. So if you have some questions during the webinar, please don't hesitate to ask them during in the chat section, and we'll answer them right after the webinar. So let's talk a bit about the different kind of industries in which CFD is used, because it's very important to know the different branches, so you know exactly where all the knowledge we'll talk about today is applied in the industry. So in electronic and electronic devices, you find a lot of CFD applications. In heating devices, fluid machinery, for example, in marine offshore, automotive, aeronautics, in plant industry, and in construction, for example. So I'll give you some example of each of this area, and also I'll describe to you why this is very useful to use flow dynamic analysis to solve such kind of problems. So CFD analysis is used first and foremost in product performance evaluation. So it helps to extract the real flow pattern inside any complex hydraulic device, such as blowers, butterfly valves, or reactors. And flow velocity and pressure can be extracted in any point. This is very useful to detect if there are some recirculation areas in your products, for example, which would lead to problems during the life cycle of the product. Now, coupling of fluid pressure calculation with structural analysis through fluid structure interaction is useful to detect the impact of the inner fluid on the product. So as you can see in this example of valve, you can analyze the flow, and then you'll get deformation and stresses on the structural model, and then you'll know how to improve your design. Heating and cooling is another big application of CFD. Flow analysis can be coupled with heat transfer for such application, and the present application, the present example, demonstrate the force cooling by fans inside some telecommunication equipment. So you know probably that all these new electronic device, there's a lot of heating and PCBs and everything, and you need to analyze the cooling of that using forced convection. So the coupling between CFD and heat transfer is here very useful. Also, CFD analysis gives some solutions to simulate easily the flow of gas or liquid into some facilities. And the present example, for example, is the analysis of the flow pattern inside a power plant factory. So in this case, CFD analysis showed very clearly that some flow separation phenomenon occurred, and gave a way to analyze quickly different kind of design that could solve this problem. So here on the left, you see flow separation phenomenon that occurs in this area. So the flow is not optimal and you have some recirculation zone. This kind of thing, actually, you cannot see it in your real model, let's say, in your real factory, because you can't observe that. Maybe you can if you use some captors or things like that, but this is very expensive and difficult to find the right position. But simulation shows such problem immediately, so this is why this is really a tool which is very useful. Now, in this example, as you can see in the picture, the addition of some thin walls in this position solved the problem and improved a lot the performance of this power plant. So with CFD, you can directly add some geometry, remesh, and test your hypothesis to see if you were true, if this is solving the problem, and you can see directly the results. So this is a great performance for your company if you're able to solve this, because it's simply you're saving a lot of money. Now, CFD simulation can also be used to analyze more complex problems, such as free surface problem analysis that help to determine the behavior of vessels and all the marine structure underwater, or problems like the sloshing of combustible in a tank, for example. CFD simulation allows not only the calculation of flow inside a product, but also outside a product. And this is where the turbulence effect that we will talk today comes into play. And such outside flow simulation gives directly the results of the pressure applied on a product. And this pressure can then be transported on the structural model through fluid structure interaction and provide to the analyst some very good and useful insight for the design. So this is what we did for this panel. So you first analyze the flow, then you get the pressure on the structural model, and then through fluid structure interaction, you have the deformation of the panel, and you can improve your design to make it more resistant, like in this case.
Okay, so now there is a time for me, let's say like this, and thank you, Saipen, for this introduction about the capabilities of midas NFX. So once again, we are doing this webinar because we received a request from your side how to make, let's say, turbulence analysis inside midas NFX, because there are a lot of parameters and some of you simply don't know how to conduct that. So basically, as I said, this topic is very wide, and we can we can cite the books, we can cite the knowledge from the books, but this is not the point. So I'm starting from the short classification of the flow types, which is related to the classification based on the fluid pattern. And as you know, this fluid flows can be classified from several aspects. So fluid can be incompressible and compressible, for example, and irrotational, rotational, and others, let's say. So today we are talking about the laminar and turbulent flow. So this classification, as I said, comes from the fluid pattern. So if you take a look on this picture, just to remind you quickly what it is, at the top situation we are observing the laminar flow, which happen, let's say, like at this example, if we consider the pipe with the let's say injection of dye into the middle of the stream, nothing is happening. So the flow is very stable. And as well, the layers of particle are parallel, but increasing the speed, for example, can cause the situation when the flow is not stable anymore, and due to several stages, like we can observe from the top situation up to down, let's say, the transitional flow occurs, and finally what we have, this is a turbulent flow, which is characterized by the presence of the eddies. So as you see, this is, as we see on the picture, this is the behavior of turbulent flow. So in the complex situations, actually, as you know, the most of the flows in the physics in the natures are turbulent. So this is why this is a challenge for the CFD analysts to model and predict correctly the turbulation areas and simulate the behavior of the fluid. So the next slide refers to the next slide refers to the Reynolds number. So that's basically the dimensionless parameter which characterizes this type of flow. So it can be interpreted like this case. So when the actually maybe let's not start from that. So if you take a look on this parameter at the top of this equation, there are several data like density, like density, diameter of the pipe, or of, let's say, characteristic dimension, um, and at the bottom we are observing the viscosity. So if you take a look on this calculation, of course it's easy to prove that this parameter is dimensionless. So depending on the value, we can judge if the flow is laminar or turbulent. And as I said, the interpretation, let's say the top of this equation stands for the inertial forces, and the bottom is related to the viscous forces. So we are using this ratio. So it can be interpreted as when the inertial forces dominate over the viscous forces, then the flow is turbulent. And in the reverse situation, when the viscous forces are dominant, and so for example for slow flow and all low Reynolds number, let's say the flow becomes laminar, and all the fluid particles are moving in line. So the laminar flow occurs, let's say, for the Reynolds numbers less than 2000 if we consider a laminar flow, internal flow. So it is characterized by low density. As we saw on the previous picture, the dye doesn't mix with the water, fluid particles move in the straight lines. And what else? It's this model, this approach is very simple to analyze from the mathematical point of view. The second stage, what we observed on the previous slide, was a transitional flow, and it occurs for the Reynolds numbers between 2000 and 4000, and it occurs for the speeds which we can classify and we can tell like medium. And this dye, as we saw, I can back to the previous slide. So this dye mixes slightly for this situation. And finally, the turbulent flow occurs when this number is more than 4000. But now I'm talking about the flows inside the pipe. So for the different situations, this number has got different values simply. So depending on the situation, if it's external flow or internal flow. So that's all, let's say, about this quick introduction. Right now, we will be more focused on the midas NFX capabilities and basic definitions. So I would like to start from quick overview about the computational techniques which are widely used for calculation of the CFD problems, actually for the turbulent flow. So some of them are known. Actually, most of them are known, and then the basic technique is called direct numerical simulation. So I didn't say anything about scales of the turbulence, but once again, I'm talking about that because we have to refer to the books and we have to have some basic knowledge before we are talking. But trust me, this is the algorithm which is useful for, which is needed for the solving of these problems. So what is doing, let's say, this algorithm? So basically, the CFD problem is solved by Navier-Stokes equations, and this algorithm resolves all the scales of the turbulence by solving those Navier-Stokes equations numerically without any turbulence modeling. So this is the direct approach. The second approach is called large eddy simulations, and this is valid for the large scale of eddies, and the governing equations are solved directly, and small eddies are modeled using, for example, semi-empirical models, and the scale separation is obtained by applying some kind of filter to the governing equation, which is the mathematical procedure. And finally, the third method is called Reynolds average Navier-Stokes, and this approach is the most widely used from the practical point of view. And the governing equations of the float are solved using an average in average form of the equations. So turbulent fluctuations are strictly related to the mean flow, and due to this, the effects, let's say, of the turbulence can be approached by semi-empirical models. So which approach is the best? That's the question that someone asked. So basically, the most accurate approach for some type, let's say, some type of the problems is the direct numerical simulation. The second approach is the large eddy simulation, and finally, the least accurate but much more often used in the practical point of view is average Navier-Stokes. So just to tell you, let's say, some kind of short story related to these methods. So there was a test which has been made a couple of years ago, and two of those approaches has been compared. So simply RANS and DNS. So the difference between the solution timing is like following. So for example, if the RANS algorithm needs 40 seconds to solve some CFD, let's say, turbulence problem, the DNS use 10 to the power of 12 seconds. Right now, actually, I haven't converted those data, but the difference is huge. So we are comparing 40 seconds to the 10 to 12 to the power of 12 seconds. So this is a very huge difference. Also, if we take a look on this picture, the top picture shows us the influence of the use algorithm, because as I said, we are using the average form of the Navier-Stokes, so some kind of information has been simply lost, but the solution time is simply quicker. So what are we doing basically in CFD? On the next slide, I'm presenting the application of the Reynolds averaging equations according to the 2D incompressible case. So this set of the equations has several forms, but the problem which has got the present in CFD simulation is to find those quantities which are called Reynolds stresses. So we simply looking for those quantities to estimate. Actually, we are looking for this we have to estimate these quantities to close the equations and get the solution. So that's the challenge, and this is why we are actually this is why some turbulence models has been developed. So this is let's say, one of the most important steps in CFD analysis, the choosing on the right turbulence model. If our flow is turbulent as well, let's say like that. So basically, there are three families of turbulence models, and they are represented by zero, let's say, algebraic models, which refer to the zero equation models, one equation models, and two equation models. So first approach is the simplest and let's say least computationally expensive. The second family is, as I wrote, is the one level up in the turbulence of modeling. And to solve, for example, to solve a problem, a single transport equation is used to obtain turbulent data. In that case, this is a turbulent viscosity. And finally, we have two equation models, and this, as the name implies, this model requires two solutions to compute the contributions of the turbulence to the mean flow. So what we have in midas NFX, actually we have I think 12 models which are available for you. So we have zero equation model, which is called mixing length. We have one equation models, like model of Brandt's model, two lawyers, Spalart-Allmaras, and two equation models with the popular ones like K epsilon, K omega, and LES based models, which means large Eddy simulation models. So just to tell you which one, let's talk about some features of those models. So if we consider, for example, one equation models, this model which is called Spalart-Allmaras is a very economical model for the large meshes. And on the next slide, I will, let's say, take into account a bit to the discussion which model should be used in which situation. But let's say, let's talk about this at this moment. So as I said, the Spalart-Allmaras is, for example, is very good for, let's say, mildly complex external and internal flows. Is good to solve the problems when we have to solve problems with the flow around airfoils, wings, ships, for example, but performs very poorly for 3D flows. So it's not valid, for example, for the flows with strong separation. The second, let's say, model, like K epsilon, which is widely used, is a model which is very robust, let's say, but in the same time, what is mandatory is to have some knowledge about the limitations of that model. And according to that, you can find the informations in the midas NFX manual. So we are writing there what kind of delimitation of that model. The next model, like K omega, shows us the superior performance for some cases where the bond layer, free shear, low Reynolds number flows are mandatory to solve. It's very suitable for the, let's say, by boundary layer flows under adverse pressure gradient and separation problems, and so on. So as I said, the biggest challenge is to select the proper model for our applications. And main question is if there is any rules of thumb exist. So basically, everything depends on your own experience, and there are 3 points which can be helpful to those of you who don't have experience with CFD. So basically, very similar to the structural problems, we should know our physics, which means we should use our engineering judgment to predict what flow features will be present in our applications. We have to get the information about the code. We have to get the information about which features our code have, and to examine the models that our code is supporting, and to study the different options. So that's the very general advice. But for someone of you, let's say, if I may to tell you something about this, the general rule of thumb, what to use for the beginning. So if you are lost, or if sometimes you are analyzing the very complex model, you can use the shear stress transitional model, which is SST model, or the Spalart-Allmaras Spalart-Allmaras model, because usually they are provide you very fairly safe, let's say, choice, and they are generally robust and provide reasonable accuracy over a, let's say, wide variety of configurations. From our experience, let's say in midas, we are often using the SST model, but let's say especially for external flows, this Spalart-Allmaras also, let's say, it's very practical. In other situations, we can use the general purpose K epsilon model. And as well, the third point about that is to take advantage of specialized models, which is we have to understand how the model works. So this is what I was telling you, is that there's a general rule, but we cannot assume simply that this model is fine and study this to each situation for the each flow and each case, because of course this is what I don't want to tell you. I'm just giving you the example for the clues for the for let's say for the simple flows. So as I told you, this, don't forget about this KE restrictions if you want to use this model, and you can refer to this our NFX manual for more information. So the next point, which is related to modeling of the turbulence, generally speaking, is near wall treatment. So that's the step, let's say, which comes after, let's say, when we have some idea what kind of flow we want to analyze, which model we want to select. The next step refers to the refers directly to the modeling. So now we have to think how to model the behavior close to the wall. This is very important because of the presence of several layers. So if you take a look on the picture, so at the close, so for as the example, if we consider the flow over the plate, actually this is an example. Some several layers exist, as I said. So basically there is a layer which is called viscous sublayer. The second is fully turbulent region, or the name is changed to log layer, and above that we have outer layer. So what are we doing? We need to model this layer very accurately to get, let's say, correct CFD result. So why we are doing this? Because we have to reflect the behavior of the rapid change of the gradient of the velocity. This is why. So it's very difficult to catch the proper behavior of this velocity gradient rate of change. So what we have two strategies, two techniques which are helpful to model this sublayer. So first is related to the resolving of the viscous sublayer. So what are we doing? We are simply generating a mesh with the more dense nodes in the normal direction to the wall. And the second technique is the usage of the law of the wall. So on the next slide, what is the behavior of that? What is the what the options we have inside midas NFX? So if we go directly to the software and if we open the definition of the wall, basically we have two options which are related to the wall of to the law of the wall. Actually, there are three options, but the first one is not visible at this moment. But I would like to consider those two options. So what are we doing? So this wall function is giving us a method which is using some empirical formulas to impose suitable conditions close to the wall without resolving of the boundary layer, which means that we are not focused on increasing the number of the nodes close to the wall. This is why we are using this empirical formulation, and because of that, we are saving the computational resources. And this is one of the advantages of the wall function approach is this. Let's say if we consider the gradient of the shear layers close to the walls, all of them can be modeled with relatively coarse meshes. Which means, if I'm showing you this, we are using this approach to provide empirical formula of this region close to the wall, let's say wall of the pipe or wall of the airfoil. But airfoil is maybe not a good example because this is related to external flow. But let's stay with this internal flow. And after that, we still have to think about the proper distribution of the mesh. But this time it can be, let's say, less dense, like in the situation that we have to do this manually. So we are using these two options. So we have Y plus definition and delta wall, which is called wall distance applied. So we have to know this Y plus value, or let's say estimate that. What is this? You can try to find the information in the books. So I'm not showing that. So this is simple formula, and a lot of literature is handling this topic. But the question is if this approach has got any limitations. So yes, as always, there is something that we have to think about, let's say like that. And as I told you, even if we provide, or even if we select the right wall approach, there is still a need to think about, to take into account this, that this function of the law cannot model boundary layer turbulence properly. So sometimes we have to ensure some additional effects like friction, for example, heat transfer or separation. And this is why this number, for example, the nodes should be increased. And typically, what we are doing in midas NFX, we are using the 10 or from 8 to 10 of the nodes to create the mesh when we are using this wall function. Okay, so and more about, let's say, these limitations, again, you can find in midas NFX manual. So the second approach is related to the viscous sublayer resolving, and in that case, I'm using the example which is related to the simple fluid flow in circular pipe. So on the situations when there is no law, or exactly this is our decision that we cannot use this law of the wall, we have to create our mesh manually. So first of all, we have to assume, we have to guess, we have to have actually the thickness of the viscous sublayer. Why? Because there is a procedure which will be helpful to estimate. Actually, this is the receipt to estimate the thickness of the viscous sublayer, because this will give us the minimum distance in the normal direction from the wall. So this is why we are doing this. And that is, as I'm showing to you, there is a collection of the formulas which refers to the additional quantities like value of the wall stress and which has got presence in this formula above, because we have to calculate this distance. So there is equation number 1. So we are looking for the friction factor. If we take a look on this equation, that quantity is something that we don't know for the moment. So the equation for that looks like following. So we have the velocity, we have density, and we are looking for this friction factor. So this friction factor can be estimated from this Colebrook and White law. But if this is, let's say, too much complex for some of you, you can use this equation, but as well in regard to some to some condition according to the value of the Reynolds number, because we have to again open the book or use some reference material to study which formula in which case is simply valid. So I'm not saying that this formula is valid for every case, but I'm using this as the example. So if we, as I said, if we consider the mesh, this let's say example of the mesh can be not adequate for our sublayer resolving. We can use law of the wall, or we can use this procedure, and in that case we can use the no slip condition. So it was all about the near of the wall treatment, which was very important step after choosing the turbulence model. The next step refers to the turbulence conditions, inlet turbulence conditions, or even initial conditions. So there is a need to estimate some quantities like turbulent intensity level. So in some codes you can define this with the inlet definition, but in midas NFX you have to simply go to the analysis case window and you can find the fields here, which is and the name is the field definition. So we are treating this as the initial condition. So there is a there is a formula which is valid for the internal flows, but due to the experience, there are some values that can be used by you, let's say, in the most cases. So as I'm reading there, for external flows over the aircrafts or the cars or submarines, the turbulence level is below 1%, but typically this value can be selected, and I will right now change the screen to the example, and I will show you the results according to this very simple flow inside the pipe. So here you have the data. So the model is axisymmetrical. So this CFD analysis has been analyzed using that feature. So the diameter is 0.2 meter, height is 8 meters, the speed is 1 meter per second, and depending on the viscosity, we are judging if the flow is laminar or turbulent. And I will show you the more details about modeling of this flow. So starting from the material, I'm going to this branch and I'm clicking on edit. So this is a data which were important for the modeling. So the flow basically is incompressible. We are using the incompressible solver. The mass density input looks like following, and the density and the viscosity has got the value as presented on the previous slide. So that's the material. Of course, we are using SI units. This is very important, as always. And at the same time, similarly to the structural analysis, we have to think about it. But this system is interactive, so you can change those units almost all the time. So the second thing is the property. So the property is looks simply like that. Why? Because the model has been presented in the axisymmetrical form. So if we go to the settings, here is the window when we can make a selection. So we are doing the selection before we start actually. So this is the first window that you will see in midas NFX. So my model is axisymmetrical, and this will be CFD analysis. Okay, so we have property, we have material, and of course the mesh. So just to show you the tool for the measurement, I'm using axisymmetrical condition, so I'm modeling only the half of the diameter of the pipe. And in this example, I'm using in considering the wall treatment, I'm using the viscous supplier method, which means that I'm trying to add sufficient number of the elements close to the wall. So this is my technique that I'm using. So how I made that. So now I will switch to the Excel file. So I'm clicking on the Turbulent. So this is my second study that I made before the model. So I inserted the data like mass density and calculated the Reynolds number. And using the formulas that I was presenting to you, I developed all of these data. So turbulence intensity level is about 0.46, and the data related to the initial conditions has got those values. So let me back again, and there is one thing that I forgot to tell you. So the first step actually is the calculation of the thickness of sublayer. So my result is close to 0.0086 meter. So again, if I go there, I should have something similar, and we can simply measure that if we snap to this. So it's even less as our condition which we've got from the Excel file. Of course, the ratio between the nodes is also important if we decide to use this method. So it should be almost 1 to 1.2. So this is not like some kind of magic number, but you have to know that the increasing ratio should be very, very low. So all of those elements which are standing next to each other should have the same size. Okay, so that's the general conditions. So if we go to the boundary conditions, there are three things to define. So basically, I'm defining the velocity at the edge. So that's the edge when my inlet has been defined. So I'm inserting the velocity of 1 meter per second. In the opposite direction, there is an outlet. There is an outlet, and the condition for that is 0 because I'm assuming the outlet to the atmosphere. So there is no need to show you that. So I'm using this, and the third condition is no slip wall. And as I told you, I'm using this technique to calculate viscous supplier manually. So I'm operating by the mesh. So that's all what I did. The last step is to go and edit, select the right analysis type. So in that case, this is a steady state CFD. I'm inserting following data, and of course there is nothing inserted in the turbulence because my model, which I'm selecting from this, is laminar. But of course, in that case, I've calculated this model. I've calculated this Reynolds numbers, and this is very easy to guess. So this presented example, of course, has no, let's say, practical usage, except of the fact that all of this knowledge has to be possessed by CFD analysts. So we have to think, we have to remember which parameter is important. And right now, I'm showing you the second model, which is exactly the same, but the difference lies in the analysis case. So in that case, first of all, I'm selecting two equation K epsilon model, turbulence model, and in the field definition, I'm inserting exactly the values that has been calculated from my Excel sheet. So those numbers are inserted there. So this is why we are, let's say, defining the initial conditions, turbulence, initial inlet conditions. So that's okay. So now just to show you some results. So when the calculation is done, clicking on this edge, we are obtaining the result. If we calculated much more quantities than the pressure, we can right click on the insert analysis results, and all of the data related to fluid flow like Y plus, vorticity, eddy kinetic energy can be added. So it's up to us. So this is the distribution of the turbulent model. So basically that's all what I wanted to show you. So I think Cyprian, do you want to add something? Because if let's say you have some questions, I would like to ask you for email exchanging with us. And again, I would like to say sorry for those people who feel some disappointment according to the lack of the important knowledge. I told you at the beginning that this is a very wide topic, and it's very difficult to assemble this knowledge in 45 minutes. But general guidance according to the solving the problems looks like following. So I'll be back to the presentation again. So every time when you are starting this, you have to guess, you have to determine, not guess, what kind of flow do you want to analyze. So we are calculating the Reynolds, we are choosing the proper wall treatment strategy, we are creating the mesh for the suitable approach, even if we are using the law of the wall method, there is a still need to calculate that. What is Y plus? This is you can easily find this in the on the website. We are making selection, and of course we have to think about reasonable boundary conditions, which stands for the initial conditions that I told you.